So we've covered chi-squared goodness of fit. Let's look at a different kind of chi-squared test. Oops, let me start the slideshow. We're going to do chi-squared test of independence. So test of independence involve using a contingency table of observed data. So think about it. It could be a lot of the ones you might have seen previously is contingency tables with if people have a disease and then if they truly have the disease, like false negatives, false positives, those kind of things. So what we're doing here is I want to test if two factors are independent or not. Remember the same thing for factors as variables. So it's very similar to a goodness of fit test, but again, I'm looking to see if these two factors are independent or not. So if your expected value of each cell is less than 5, you have to use a Fisher's test. We're not going to worry about this in this class, but I will tell you this. You run it the exact way. Hypotheses the same. It's just instead of doing a chi-squared, you do a Fisher's test. It handles those low values, and it does something a little bit different to handle them. So suppose factor A, so this is a variable, a speeding violation in the last year, and B, another variable, is a cell phone user is while driving. So this is what I'm looking at. Event A is that the person had a speeding violation. Event B is they used a cell phone while driving. So if I want to know if speeding and cell phone usage are independent, then I'm going to use this probability formula that hopefully you might have seen sometime in the past. So it's going to be the probability of A and B equals the probability of A times the probability of B. So what does that mean? It means for me to know if they are happening to each other, then I do A times B. Okay. So again, A and B is the event the driver received a speeding violation last year and also used a cell phone while driving. So suppose that in a study of drivers who received speeding violations in the last year and who used a cell phone while driving, that they surveyed 755 people. Out of the 755 people, 70 had speeding violations, 685 did not. 305 used cell phones while driving, and 450 did not. Okay, so I need to solve this problem. So let y equal the expected number of drivers who did both. They used a cell phone and they got a ticket. So, all right, remember, probability of A. And let me go back to this one just so we can look at it again. Remember, probability of A was a speeding violation. And right here, it says 70 got a speeding violation. So that's going to be 70 over 755. So B then is cell phone users while driving. So remember, 305 cell phone users use their cell phone while driving. So I've got 305. So that's what we did. We put 70 divided by 755 times 305 over 755. And if we solve that for y, you get 28.3. So those are the expected number of people who used their cell phone while driving and received a speeding ticket. You do not have to worry about doing this by hand. I just wanted you to show you where the math is coming from. So in a test for independence, we state the null and the alternative hypothesis in words. Since the contingency table contains two factors, and again, I'm using factors, but basically I'm talking about variables. The null hypothesis states that these factors are independent, and the alternative hypothesis states they are not independent, okay? Null is saying they're independent, alternative is saying they're not independent. Not independent is another way of saying they're dependent. They depend on each other to happen. When A happens, then B happens, vice versa. If we do a test of independence using the example, this is what the hypothesis says. The null hypothesis is being a cell phone user while driving and receiving a speeding violation are independent events. If the null hypothesis was true, we would expect about 28 people to use their cell phone while driving and receive a speeding ticket. Right. The test for independence is always right-tailed because of the calculation of the test statistic. If the expected and the observed values are not close together, then that test statistic's going to get really large, and it's going to be way out in the right tail of the chi-squared curve. That's the same as it was in the goodness of fit test. So one way that we do number of degrees of freedom for a test of independence, it's the number of columns minus 1 times the number of rows minus 1. You don't even have to worry about it because Minitab does it for you. So the following formula calculates the expected number. So the expected number is the row total times the column total divided by the total number surveyed. But you don't have to worry about that because, again, Minitab does it for you. All right, let's look at the first example that we're going to do. In a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with disabled senior citizens. This program recruits among community college students, four-year college students, and non-students. In the table, there'll be a table on the next slide, is the sample of adult volunteers and the number of hours of they volunteer per week. Okay, sorry. So the table is just showing it's a sample of the volunteers and the number of hours they volunteer each week. Is the number of hours volunteered independent of the type of volunteer? Okay, remember I've got 3 types: community college, 4-year, and non-students. And then I want to know between those 2 groups, is there any difference in the number of hours they volunteer? Okay, so here's my table. All right, so community college students. It's showing here that like 111 volunteer between 1 and 3 hours, 96, 4 to 6, 48, 7 to 9, and this is the row total. This row total is for the community college students total. Same, so for 4-year, I can go across and see it. 290 is the number of 4-year college students I have. Non-students is 294. If I go down, this 298 is all of the 1 through 3 hours. People who donated their time that much, I had 298 of them. 4 to 6 hours, 379. 7 to 9 was 162. 839 is the total number of people who are in this table. So again, 3 different groups, 3 different hour designations of volunteering. This is a contingency table. Okay. So let's see this. All right. Remember, my question was, is the number of hours volunteered independent of the type of volunteer? Okay. You see independent in there? That tells you it's a test of independence. There's nothing harder than that. If I want to know if 2 factors, if they're depending on each other or independent, that's where I'm going to use this type of test. Okay. Again, the 2 factors are the number of hours volunteered and the type of volunteer. So the number of hours volunteered is independent of the type of volunteer. The alternative, the numbers of hours volunteered is dependent on the type of volunteer. Okay, here's my table, but remember, I don't have to worry about much. So in Minitab, all I have to do, I don't even have to put the totals, I just have to put the raw data. I'm not going to put the rows. Let me see if I can make this a little bit bigger. I'm not going to put the rows at all. All I'm putting in is I'm doing my columns and I'm just putting my data. Again, don't put your totals in because it will count them and you don't want them to count it. And as always, remember with these slides, I have the directions for what to do. Okay, so this is what you're going to do. You're going to go to Stats, Tables, chi-squared test of association. Okay. All right, I don't have raw data. I have summarized data. So the columns I'm going to put, I'm going to go 1 to 3, 4 to 6, and 7 to 9. Okay, everything else I'm good. I don't have to do anything else. Everything is checked. And see right here, statistics, it knows it's running a chi-squared. So I hit OK. And look what it did for me. Okay, this looks a lot like what we had before. All right, remember I didn't put my totals? Well, Minitab does it for me. I don't have to worry about it. So remember in chi-squared, we had those expected values where I would find, it was that thing where here's my observed, this is what I expect. So here is my actual, let's say for this one was 111. This is what my expected should be. It should be 90.6. So the top is the observed, the bottom is the expected. It's just like chi-squared goodness of fit. But if I keep scrolling down, look what it gives me. It gives me, and we're going to use this Pearson number. We're going to get our chi-squared value of 12.991. Degrees of freedom is 4. Remember, you don't even have to worry about that big old long formula. It's given to you here. And my p-value is 0.011. Right, so let's go back and see what I got. Got everything I needed. And again, here in the slide, so you see it. And I did it here. I highlighted it. All right. I'm looking at the Pearson chi-squared. Pearson is most common. So for this class, let's look at this one. There's slight differences in the likelihood ratio, but for this one, let's look at Pearson. So again, my test statistic was 12.991. The distribution is chi-squared with the little 4 because the degrees of freedom is 4. How did I get that? Minitab gave it to me. I didn't have to do anything else. All right, so let's do our conclusion. P-value and conclusion. All right. Since no alpha was given, I'm going to assume it's 0.05 is my level of significance. So my p-value is 0.011. I got to get rid of that 3 because that wasn't given to us. Okay, so 0.011 is less than or equal to 0.05. Remember, if you get confused, add an extra 0. It doesn't hurt it. And now I can see 11 is definitely smaller than 50. So since this is a true statement, I reject my null, which means my factors are not independent. They're depending on one another. So at the 5% level of significance for the data, there is sufficient evidence to conclude that the numbers of hours volunteered and the type of volunteer are dependent on one another. That's all that means. And as you can see, what changed from chi-square goodness of fit? A little bit, we had to do a little bit different with the data, but now we're looking at 2 different variables. I still had to make 2 hypotheses, my independent and dependent, and then I ran it through Minitab, got my test statistic, got my degrees of freedom, and I got my conclusion in that by that p-value. That's all you're doing.